Okay, welcome to the week 9 webinar. So this is the webinar all about the chi-square distribution. And let me share my desktop and show you the plan for the day. Okay, so the plan is to start with questions and answers, as we always do. Always happy to answer any questions you might have. And then we're going to do the chi-square distribution. Kind of show you a picture of it. The math is way too hard to, do the math, but hopefully you're used to the fact that you can just trust the calculator and it'll give you what you need. But I'll at least show you a picture. And then I'll show you some hypothesis tests that will use this chi-square distribution for different things. So the 3 hypothesis test types that we're going to be looking at today are the chi-squared goodness of fit test, the chi-squared test for independence, and the chi-squared test for homogeneity. So that is a plan. Just a reminder at this point, the hope is you have your project ideas at least thought out a bit. I'm still waiting. I'm watching the project 2 discussion board often. Please post your project 2 idea on the project 2 discussion board so that I'll be able to look at it and help you out and tell you if it's going to work or not. Just let you know, the project 2 does not involve what we're talking about this week. So if you think you're using the chi-square distribution for project 2, think again. Project 2 really is all about chapter 10. It's all about confidence intervals and hypothesis tests for a difference between 2 means. Either independent or dependent, that's your choice, but you pick one of those, and that's what the project is about. So, make sure, in not too long from now to have a project idea, post it on the project 2 discussion board, and I'll take a look at it, let you know if it works, give you some suggestions on improvement, etc. So any questions about anything? Any questions? I'm watching the chat box. Also, welcome to unmute yourself and talk if you have a question. Either way. I don't see a lot of questions. This might be a shorter webinar than usual because we're not like going over a test and, we're not talking about some kind of test or talking about the project or anything like that. But we do have chi-squared. So just a note, I've got this right up here on the screen, and that is chi is actually a Greek letter. And, don't shoot the messenger. I'm not the one that decided that that's the letter they should use for this stuff, but it's what everyone uses. And so that it kind of looks like an X. It's kind of a curvy looking X, but it's actually a chi and not an X. So when you hear chi-squared, you have chi and then squared. And the squared has something to do with the math that's happening. It turns out that with the chi-squared distribution, you don't get any negative numbers. And when you square a number, you don't get negative numbers. So it has to do with that square. Again, you don't have to know the math, but I figured maybe I should explain a little bit on why they call it chi-squared. I do want to show you a picture. And I actually created an app that shows the chi-squared distribution. Does this look like the normal distribution? What do you think? Does this look normal? You can kind of see the distribution. Yeah, not quite. Do you remember how to describe a distribution like this? I know it's been a while since we went over the shapes. Remember? Okay, I don't see y'all jumping in. Well, it's unimodal because it definitely has one peak, and it's skewed right because it has kind of a tail on the right-hand side. This is degrees of freedom. DF stands for degrees of freedom. And this This one that you're looking at is 3. If you change the number of degrees of freedom, it actually changes the picture a little bit. And if we go to 6, then it looks like that. You'll notice that there's nothing to the left of 0. It just stops at the origin. And that's important. One of the things that makes life easier is that we're not going to be doing a two-tailed test or a left-tailed test. It's just a right-tailed test. That's all there is, because there is no left tail. There's only right tail. So it means that you don't have to worry about that at all. If you have lots of degrees of freedom is going to have something to do with how many choices someone has in the answers, they might say. And if they have a whole lot, then that's what it looks like. It looks a little closer to normal, it turns out. But that's the shape. Any questions on the shape? Okay. Again, the math of the equation for this is way too hard for this class. So right now, just want you to see it. So when you have a p-value, it's going to be the area to the right, because it's only right-tailed, of whatever the value is. And that'll be the p-value. Okay, so I just wanted to show you that. Let's get back to talking about this stuff. And I want to remind you, when we looked at chapter 8 and 9 and 10, and you looked at the survey question, there was a survey question that was quantitative, so that would be a number answer. Things like, how much do you weigh? That's quantitative, right? You weigh 170 pounds or something. Or maybe, I don't know, how many siblings are in your family? That's quantitative. We also looked at a different type. We looked at a yes-no survey question. That would be something like, will a student pass this class? It's either they pass it or they don't pass it. Okay, that's a yes or a no. So that's an example of a yes-no question. Are there any other types of questions of variables that other than quantitative and yes-no? So are there any other types? You can pop in the chat or say it, one or the other. I'm watching the chat. Any other types of variables that come from a survey question? Okay, or data collection, besides quantitative and yes and no? I don't see y'all jumping in. You'd say there aren't or there are, you choose. You got a 50-50, right? You have no idea. Other types. I don't see you jumping in. I want to give you a chance because it's important to understand the different possibilities for variables that could happen in data collection. All right, well, if I don't see you jumping in, maybe I'll just mention it because I don't want to wait forever. And that is yes. Yes, there's definitely another type. So for example, let me ask you, what state or country, if it was in the United States, were you born in? Put it in the chat box. By the way, this isn't recorded. The chat box isn't recorded, so we'll know. And what state or country were you born in? By the way, I was born in California. Okay, AL, Alabama, Arizona, and California. Okay, so notice in another California. Okay, so notice that the answer to that question is not yes or no. None of you said yes or no. You didn't give me a number either. You didn't say 73 or something. You gave me a word. And there are many, 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 many studies where you're looking at a single word or type answer that isn't yes, no, and it isn't a number. And the state you were born in is one example of that. There are many, many other examples where you have a qualitative not yes or no survey. That's what we're talking about. So what state were you born in? Another one might be, what is your race? Okay. You might say Hispanic, or might say Black. You might say, white, non-Hispanic. So that would also be one, and that's asked a lot in surveys. And that would be another example of a qualitative not yes, no question. And I can go on and on and on. There's so many of them. What's your first name? That's another one. Okay, very qualitative, not yes, no. So what we want to do is we want to run statistics on that type of data. Any questions on this idea? Any questions? Okay, I think the best way of doing this is by examples. So I'm going to do some examples for you, and we'll talk about how you can perform statistics on these examples. So here's an example. I think I'll make it a little bigger font so you can see it better. Okay, so in California, I looked this up today, 39% of residents are Latino, 35% are white, non-Latino, 16% are Asian or Pacific Islander, and 10% are other races. Okay, so now one question we might have is the distribution of race is different for California community college students. Okay, because one of the things that we hope to do at our college is we hope to represent, have students that represent, who we are. And so our goal is we're trying to make sure that we have good diversity and that, every group is represented. That's one of the things we'd like to have at our college. So a survey was done of 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. What can be concluded at the 5% level of significance? Okay, any questions on the question? Okay, can this be done using, say, the chapter 9 stuff? A hypothesis test for a mean, or chapter 10 for comparing two means, or hypothesis test for a single population proportion or comparing two proportions. Would those work for this example? Would one of those hypothesis tests work? So what's your thoughts? And if so, which one would work? And if not, say no. So what do y'all think? Okay, so the thought is no. And the answer is no, because there is no mean here. There's no average of anything, because there's no quantitative numbers. The survey question is, what is your race? And you might say, my race is Latino, or you might say my race is, Asian Pacific Islander. Okay, it's not a population size. That's not the issue, actually. The population size was 300, and that's enough, typically. So that's really not the problem. And if you look at the answers, we had over 5 for all the different answers. And in fact, that's something we're going to need for what we're doing today, is we want to make sure that the expected number of yeses, of each category, needs to be bigger than 5. And that isn't a problem for this example. But the bigger problem is this isn't a yes, no question. So you can't do proportions. It's not a proportion of something. It's, a bunch of proportions combined. And it's not a quantitative, number answer question. Does that make sense? So the good news is we don't have to give up. The good news is there were some statisticians, way back when, that came up with a way of looking at a question like that and deciding how to statistically analyze it. Any questions on that idea? So let me show you the process of doing that. So the first thing, and you're used to this, is we need a null hypothesis and an alternative hypothesis. Okay, hopefully you're used to this at that point, because we do a lot of null hypothesis and alternative hypothesis in the last few weeks. But I want to let you know, in this chapter, we're in chapter 11, the chi-squared test chapter. Unlike all the other chapters that we've had for hypothesis tests, the null hypothesis and alternative hypothesis are going to be written in words. Okay, we're going to write a sentence. So it's not a bunch of symbols like we had with mu and p and that kind of stuff. But now we're going to write words. So let me show you the words of this. So H naught is, the idea is California, the community college student basically look like California, right? That's what H naught is. But let me write it in formal words, and that is the distribution of races at the California community college system is the same as the distribution of races in California. Any questions? Any questions on H naught? Maybe I'll make it a little bigger so you can see it better. Any questions? Okay, the good news is that H1 is very similar with a couple words changed. What do you think is going to change? Remember, H1, it's kind of like a debate. H1 saying, hey, the distribution is the same. What do you think that's H naught. What do you think H1 is going to do? What's the other side of the debate? Any thoughts? Yeah, it's not the same. Okay, and so the good news is I can save a lot of time. And since this is an online class, everything you do is on a computer too. You can copy and paste. And then just say the distribution of races at the California Community College system is not the same. Add the one word not, and then it works. Not the same as the distribution of races in California. Any questions at all on the null hypothesis or the alternative hypothesis? Okay, I want to highlight something, and that's the word distribution. When you're doing this kind of test, the word distribution needs to be there, because really that's what you're checking. You're looking at the distribution of races. So as you're used to when you take the exam in a couple weeks, we're in week 9, so there's no exam this week. By the way, there's no exam next week either. How come? Because I forgot to mention this. Why is there no exam next week? Even though it feels like it should be, since there's none this week. Anyone know? Yeah, Thanksgiving. Not only is there no exam, because I want to mention this, there's no class, there's no assignments. You get to take a rest if you want. So next week is a total break week. Just let you know that. There will be no webinar next week. There's nothing that you have to do. And by the way, I won't have office hours next week either. The only thing I will do, just because it's hard for me not to, is that if you send me an email, I'll answer it. But other than that, there's nothing next week. After Sunday night, you'll have a whole week of to just enjoy. I like to say your homework next week is to gain weight, because that's what we're all supposed to do on Thanksgiving. You're supposed to eat a lot. So your homework next week is to gain weight, and that's it. Sound good? Okay, so just let you know that won't happen, but the following week you'll have an exam. Okay, just let you know that. So I figure I should mention how the calendar works. Any questions on H0 and H1? Okay, so this kind of test where you're looking at, we have a known distribution. So we know what the California distribution is. And we're going to take a sample of some other thing and see if it has the same distribution as a known distribution. And the hypothesis test that we've got with this H0 and H1 and the way we're going to deal with it is called a chi-squared goodness of fit test. Okay, and the reason why we call it a goodness of fit test is we want to say, does the distribution of our sample fit the population distribution of what we're testing for? Any questions on that? So this is called the chi-squared goodness of fit test. It checks if an unknown distribution fits a known distribution. And the typical known distributions you'll see sometimes, one is something given like I did on this example. But there's also some distributions that we've had in our class already. What are some distributions we've had? We haven't had too many. Yeah, normal. So sometimes you can use the chi-squared distribution, the chi-squared goodness fit test to see if you have a normal distribution. And the other one that you often use is uniform. So are they all the same? Because that's uniform. But this example is some known population that you can look up. Okay, and you can do what I did, go to Google and see you get the same percentages that I got when I looked it up. Okay, so here's the way it works. After you've written the null and alternative hypotheses, the next thing we're going to do is we're going to create a table. And this is called the observed and expected table. So I use the letter O for observed and the letter E for expected. That's pretty standard. And for the observed, we look at what the sample gave us. So for the Latinas, there were 125 Latinas, so I'm going to type in 125. For the whites, there were 92 whites, so I'm going to type in 92. For the Asian Pacific Islanders, there were 33 of them, so I'm going to type in 33. And for the others, there were 50 of them. So let's type in 50. Any questions so far? Okay, so that's the easy one because you just type in the numbers that were given. The other one's not so hard. You just have to kind of understand what to do. We got to say, well, if H0 is true, so if the community college system was the same as California, and you surveyed 300 California community college students, how many would you expect? E stands for expect or expected. How many would you expect to be Latino? And the idea is that 39% of all California residents are Latino. So if you surveyed 300 people in California, you would expect 39% of them to be Latino. Does that make total sense? So if you expect 39% of the 300 people to be Latino, how many people would you expect to be Latino? How do you get that? What basic math do you have to do? Yeah, you take 0.39 times 300 and you get 117. So that's your expected. for the Latinos. So we do the same idea. We're going to take 35% of 300. And how much is that? You can use a calculator. I did in my head, but I got 105. Any questions on how I got that? Maybe I should type out what happened. It's in the chat box too, because we had a student that actually came up with it, which is nice. So notice that 0.39 times 300 was equal to 117. And then we had 0.35 times 300 was equal to 105. And then we're going to do the same thing with the Asian Pacific Islanders. We're going to have 16%. So 0.16 times 300. That's equal to what, 48? And then the same thing with the others. That's 10%, 0.10 times 300. And that was equal to 30. So let's put those numbers in. So we're going to have 48 and 30. So let me stop for a second. Are there any questions on how I came up with this observed and expected table? Any questions? Okay. And just a note, if any of the expecteds aren't bigger than 5, you can't really do this test. The sample size is too small, and we're used to that, is that if you have too small sample size, then you just give up and maybe get a bigger sample size. Okay, but this example, big enough sample size, no problem. Any questions so far? All right, so then the next step, there's a step you're used to, is to go to our calculator. And which calculator number do you think we're going to use? Yeah, this is a chi-squared goodness of fit test. Okay. And I want to let you know, by the way, we're getting close to the end. So as I mentioned a few times, I wrote this calculator in the order of which we do things in class. So you can see we're almost done. The light is at the end of the tunnel. There's only 25 calculators that are used, and we're actually doing 21, 22, 23 today. There's only 2 left. So we're almost done. So I'm going to go to goodness of fit. And what it says is type in the values of the observed and expected set separated by commas, and then hit calculate. Try to make it easy. So we're going to have the observed. So I'm going to go to this guy. Going to copy and paste and put some commas in. Notice there's no commas. If there's no commas when you copy and paste, you need to make sure there's commas. Because I remember someone was having trouble because someone forgot to put the comma in their discussion post last week. And that doesn't mean you can't do it. It just means you got to remember to put the comma in. So any questions on the observes? Okay, then we're going to go to the expecteds. And put some commas in. Any questions so far? Okay, and again, I tried to make it easy. You just hit calculate and it does everything for you. Okay, so the test statistic is a chi-squared test statistic. Okay, it's not Z, it's not T. Now we have a new one. And the new one is chi-squared. And I showed you a picture of that, at the beginning. So you get the idea. And by the way, there's that thing called degrees of freedom. If you take the number of categories, we had 1, 2, 3, 4 categories, and subtract 1, that's 3 degrees of freedom. So if you ever ask for the degrees of freedom, take the number of categories and subtract 1. Okay, so chi-squared is 20.18 or so. So I'm going to write that in. And the p-value is 0.00016 or so. Any questions on getting the test statistic and the p-value? Are you starting to see that this hypothesis testing really, it's kind of the same process? There's little variations, but there's always, you're right, you enroll in alternative hypotheses, you look at the data, you put in the calculator, you get a test statistic and a p-value, and then you state the conclusion.
I do have one question.
Sure.
So for when we're referring to the mean, the variable we use is mu, and then for the probability or proportion, it's p. Is there like a letter or a Greek letter we would use for the distribution?
That's a really good question. And the answer is no, which is why you'll notice I told you we do this in words. There's no real symbols. There's no real symbols to use. So that's why you got to write it as a sentence. Yeah, it's a good question. And so this week, there's no symbols. It's just going to be words. So get used to it. And I super highlighted distribution. So when you're doing goodness of fit, the word distribution will always be there. And I'll get you started, by the way. So it's the distribution of the observed is the same as the distribution of the expected. Really, that's what this H0 says. And yeah, we don't use symbols for this one. So good question. Okay, so now it's time to state the conclusion. The good news is hopefully you all know at least the first few words of the conclusion when we have a p-value of 0.00016. And what are the first few words of the conclusion? Nothing's changed in the last few weeks. What's the first few words? Yeah, there is statistically significant evidence to conclude. Okay, nothing changes. It's still that because p is small. Okay, and by the way, when p is really small, less than 0.01, then you can use the word strong if you want to. But that's up to you. So but if the p-value is bigger than 0.01, don't use that word strong. But there is statistically significant evidence to conclude that. And now the good news is this is an online class, so you're doing it online too, so you can do exactly what I'm about to do. And that is take H1, copy it, and paste it in. Okay, and maybe make the font size the same. Sorry.
Sorry, Larry, I'm going to take off, but I'm going to update the class in an announcement about my schedule next week.
Okay, thanks, Braulio.
So, yeah,
and just let everyone know Braulio's there to help. He's got lots of tutoring hours, so definitely.
I haven't decided on the hours yet, but I think I'll hold something for next week, just in case anyone has questions.
Oh, for next week? Okay, you don't have to, but
okay. Well, I'll see.
Yeah,
right,
yeah.
Thank you.
Okay. That's right. I forgot about next week. Yeah, the next week's a whole different life. Okay. So any questions on the conclusion? So once you've written your H1, it's really easy to do the conclusion. It's either statistically significant evidence or there's statistically insignificant evidence to conclude. Any questions at all on the chi-squared goodness of fit test? So the problem is that you never conclude H0, right? Yeah, you never ever in any situation in any of the hypothesis tests in any of our chapters do you ever conclude H0. You always conclude either you conclude H1 or you say there isn't enough evidence to show H1. You can never say H naught is true. That makes sense? Okay, but good question. It's an important one. Okay, so that's an example, goodness of fit. Again, I don't want to, torture you for too long, so I give you one good example or try to of each type of question that we'll have. So now let's move on to the next type. And that is does it matter what season a person was born when it comes to the type of car they drive? The table below shows the season and type of car. Okay, so that's the old, kind of the astrology thing. I don't know if any of you are into astrology, but they've done a lot of tests to see, like, kind of this is season, but same idea, So, if you're a Sagittarius, is that going to mean that someone knows something about you because you're a Sagittarius? That's going to make your personality a type that maybe drives a sedan instead of an SUV. Okay, so there's a lot of studies about this stuff. Okay, and this is an example. I do want to let you know, and I probably should give you the heads up on the last one too. These numbers, I said a study was done. A study wasn't really done. I made this up, but a study could be done. You can imagine a study being done. And same thing, I made these numbers up too, but you could do a study like this. So what this table is a survey. You can imagine a survey being done where they're going to ask the person 2 survey questions. The first survey question is, what season were you born in? Spring, summer, winter, or fall? And then the second survey question would be, what kind of car do you drive? And that is a sedan, an SUV, or some other kind of car. Okay, notice that now we've got 2 survey questions, and both of these survey questions are qualitative and not yes, no. These are, just wordy answers. Any questions on this particular kind of survey? Okay, this isn't a goodness of fit, because the goodness of fit is saying the distribution of something that is unknown is the same as the distribution of something that's known, and that's not what this is. This is looking at 2 different survey questions and seeing if there's any relationship, okay, between the answers to the 2 questions. Any questions on this idea? Okay, so when we have this, we're going to use what's called the chi-squared test for independence. So it's called the chi-squared test for independence. And we're going to use this test when there are 2 survey questions that are both qualitative. And we want to see if they are independent or dependent. Any questions on that? Okay. So now it's time to do what we're used to doing, and that is start out by writing down the null hypothesis and the alternative hypothesis. Okay. And again, I don't expect you to be able to do this until you see me do an example, and then you should be able to do one. So H naught in this case is going to be the season a person was born in, and the type of car they drive, are independent. Any questions on H naught? Okay, how do you think H1 is going to differ from H naught? How do you think the alternative hypothesis will differ from the null hypothesis? Yeah, it's going to be exactly the same, except the IN go away. So I'm just going to copy and paste. So much easier than retyping the whole thing. And then I'm going to erase the IN and say the season a person was born in and the type of car they drive are dependent. And let me do the following. I like to highlight the parts that are like necessary. And the word independent for H naught is necessary. And the word dependent for H1 is necessary. Okay, and when I grade this, in a couple of weeks when you have to do your test, or when I look at your answer to the discussion post, your reply, you're going to have one of these chi-squared things. You're going to have to pick the right chi-squared type, and then you have to use the right verbiage, right? You have to write the words. And if you're doing a test for independence, you got to have independent for H naught, independent for H1. If you're using goodness of fit, you have to have distribution. So those are some of the keywords. Any questions at all on the chi-squared test for independence, H naught and H1? Okay, what do you think the next step is going to be? The hope is because it's kind of the same process we've been doing all along for weeks now. Yeah, we're going to go to the calculator. Let me go back to the calculator menu. And what calculator number do you think we're going to use? I tried to make it really obvious in terms of like naming these things. Yeah, this is 22, test for independence. Okay. And by the way, just let you know, the way I created this is that if you had more than a 4x4, if you had, say, a 7x7, this calculator won't work. But I'll never give you anything on your test or examples where you need that. Okay, that's the good news. Okay. By the way, if you had, say, 5 columns and 3 rows, you can always just switch rows and columns. It's called the transpose. You just kind of switch out what you're doing, and that works. So if you need to do this with like 5 columns and 5 rows, this won't work. Any guess on what you could do if you had if it was 5x5? And you might guess, you might not. But you have to have a good memory. I don't see you jumping in. Okay, so here's what you could do. You can use the spreadsheet program that I created for your projects. That has actually everything we do in class, and that will work with more columns and rows. So just let you know. But it's not going to happen in our class, but like in your future someday, if you need to do a chi-squared and you had more, more than 4x4, if you had a 7x6 or something, then you can use that spreadsheet program. Okay, but we don't need to, because that's not what we've got. We got 3 rows, 4 columns, and 73, 81, 76, 78. So 73, 81. It does take a little time to type them in. And then 76, 78. And then the next ones were 65, 68, 62, 64. And then the next ones were 43, 51. And then 48, 50. And just leave the rest of them all blank. Any questions at all on entering the table? Okay, once you do that, it's easy. You just hit calculate. All right, we got a chi-squared of 0.48. And we got a p-value of 0.998. So hopefully you're all there and you know what that p-value tells you. So what does it tell you? What's the first few words? So remember what the first few words of the conclusion are when you have a p-value of 0.998. So you remember, same that we've been doing the last few weeks. We already did 2 examples, or 1 example today. Okay, there's statistically significant. This is like as big a p-value as you can imagine getting. That's a hint. So I'll at least write the first part. There is statistically, yeah, insignificant. Statistic. That's too many STIs. There we go. Insignificant. Evidence. To conclude that, and the good news is, I can just take H1. I can copy it. I can paste it. Make that the and make it lowercase because it's. There is statistically insignificant evidence to conclude that the season a person was born in and the type of car they drive are dependent. Okay. By the way, I will let you know that I did make up these numbers, but I have done some research and I've looked, they've done some statistical tests on astrology. And they've never shown any statistically significant evidence for anything when it comes to personality and what stuff people do. But if you want to believe in it, you can believe in it. But just let you know, the statistics have never backed it up. So just let you know that, yeah, it doesn't really matter what month you were born in. You're not going to tell you your personality. Any questions at all on this conclusion? Any questions? Okay, so here's another example. Do single men and women take the same type of vacation? Okay, table below shows the results of a study, and they looked at people that said they were male and people that said they were female. And we looked at different types. You could either be an international vacation person. You could be an out-of-state person. Or just local, you know. Maybe you just go down the block and hang out. Okay, and we have male and female. Okay, this is different. It's very similar to test for goodness of fit test, except for goodness of fit test, you have 2 groups. One, you know the population's distribution, the other you don't. And you want to see if the one you don't know is the same you know. But here we have the 2 groups, we have the men and we have the women. And we don't know either of their distribution of travel types. And we want to say, is their distribution the same as each other, but we don't know either of them. So it's not comparing a known to an unknown, it's comparing an unknown to an unknown. Any questions on that idea? Okay, when we are in that situation, then the test we're going to use is called a chi-squared test for homogeneity. And you've probably heard the word maybe homogeneity before. You've probably heard the word homogeneous. Do you know what that means? Yeah, of one type. So if you're homogeneous versus heterogeneous, means kind of all mixed up. So the idea is you're testing to see if the type matters or not. Do you see that? If the male's distribution is the same as the female's distribution. So just like we've been doing for the last two examples, we're going to have words for H0 and H1. And that is the distributions of travel type or vacation type are the same for men and women. Okay, whereas when we had a good as a fit, you would say, you know, is this the same as the known one? But here it's we don't know either. So just are they the same as each other is all you can say. Okay, here's the good news. H1 should be really easy once you know H0. How does it change? Yeah, I just have to put the word not in, which means I'm going to do this. And hopefully you're noticing I'm going to do this a lot. Copy and paste. Copy, paste, and adjust. And all I do is put the word not. Okay. And the distributions of vacation type are not the same for men and women. Okay. By the way, if you want, if you know, this is English, not math, but instead of saying not the same, you could say different. Means exactly the same thing. But if you're doing the copy and pasting, it's a lot easier to type in the word not. Any questions at all on this chi-square test for homogeneity? Okay. So next step, hopefully you all know, is to do what? Yeah, we go to our calculator. So now we're going to go to the calculator. And what test are we on? Yeah, 23. And just to let you know, there's only two more. So we are very close to being done with this class. By the way, do you think there's only two more statistics tests and that's it in the world, in the universe? Oh, no. Yeah, exactly. There's a lot more. But if you remember the name of this class? Elementary statistics. So if you decide, I want to give you a heads up, if you decide to take a course as an upper division student or graduate student, that's more of an advanced statistics course, then you're going to get other tests that you're going to have to deal with. Okay, just let you know, I want to give you a heads up that just because we just did, you know, these 25 calculators doesn't mean there's not more stuff. So there's more stuff in the universe. And in fact, I've done consulting work and I had to I made my own test up. Okay. I had math to back it up. So it wasn't like just making something up off the top of my head and, you know, nobody's going to listen. I was able to, you know, write the whole mathematics of it and show that it worked and it was reliable. So there's a lot of different tests in statistics, but we're almost done with what we have to do in our class. So we're going to do the test for homogeneity. Okay. So on this one, it says enter the observed values for each of the two samples, A and B, hit calculate, and then the chi-square test statistic and p-value will be calculated for you. Okay. So hopefully you're noticing there's, you know, a lot of similarities between these three tests. They all have a chi-squared and a p-value. That's the main thing. And they all have to do with qualitative, not yes, no survey questions. Okay. So now we have to go back and we have to put the numbers in 29, 38, And by the way, if you use a calculator, I use a tab key to get to the next one. You could also use your mouse, but whatever works for you. Then we had 4742. And then finally, we had 3336. Any questions on that? Okay. And just let you know, I made this calculator so that if you had more than what, 3, 6, 9, 10 types, this calculator won't work. But the good news is that's not going to happen on anything you have to do in our class. But I do want to give you a heads up. Then you need this, like the spreadsheet program I made or something else. If you're doing it for, if you're getting a master's degree and you have your own thing that you're doing for your master's and you need more categories than what I've got, then, use a spreadsheet, just a note. But that won't happen for anything we do in our class, so this will work. So I hit calculate. We get the chi-squared is 1.4. The p-value is about 0.5. Any questions at all on using the calculator and arriving at the chi-squared and the p-value? Okay, I am hoping that you can all tell me the first few words of the conclusion. You might even be able to tell me the whole thing, but at least the first few. Yeah, there isn't statistically significant evidence. I usually write statistically insignificant, but isn't is fine. I wouldn't take off points for that. So there is, let's make it big enough. There is statistically insignificant evidence. By the way, sometimes you'll see insufficient evidence. You'll also see that, or there isn't statistically significant evidence. There's lots of ways of saying the same thing. To conclude, that, and hopefully you're used to it by now, all I have to do is take H1, copy and paste. That's a good thing about wordy H0 and H1 is you only have to write it once. Because you can copy and paste, except I made it too big, I think. And then I got to take that T and make it lowercase. That the distribution of vacation types are not the same for men and women. Any questions? Any questions on this chi-square test for homogeneity?
I do have a question. So we use the p-value to decide whether there's statistically significant evidence or statistically insignificant evidence, right? So how can we, what is, I guess, the significance of the chi-squared value in this case? Like, what does it tell us?
Yeah, that's kind of complicated. It's a good question, but it's a tough one. So let me go back a chapter. And remember the test statistic for proportions, for example, was Z. And that was like a Z-score. Does that make sense? So this example, we have a chi-squared of 1.4. And here, I'll let you know that the here we had actually 2 degrees of freedom. Because remember, it was 3 different choices, -1 is 2. Then if I go here and I use my chart, one more, the 2 degrees of freedom. And then I looked at the 1.4, that's a chi-squared. Here it is right about there. Do you see my mouse? Now, if you look at the area to the right of 1.4, That's a big area. Do you see that? So the chi-squared is that spot, is that placement on the x-axis. So we'll call it the chi-squared axis, actually. At which, to the left of that, below the curve, is the area that will be the p-value. Do you see how that works?
Yes, that makes sense.
Now, finding the area, if you had to do that mathematically, is way, way, way too hard for this class. So you don't have to, you can just trust me that I did it for you with the calculator. Sound good?
So is there a specific function for the chi-squared distribution?
Oh, yeah.
I assume it's pretty vague.
It's, I wouldn't use the word pretty, it is brutal. So it's way too hard for me to even talk about, like, even if, we wanted to go another half an hour for this webinar, I couldn't even get to it. It would take longer than a half an hour to even get into it. So calculus isn't even enough. Just to give you an idea. It's really hard mathematics. But if you want to be a math major, then you can learn about it. I've learned about it. But it's really hard. The normal distribution is hard enough. Chi-squared is much harder. Just let you know that. So we're not doing it. Sound good? But you could, go online and look, but I will let you know it'll, it is very mathematical, like not algebra mathematical. It's really high level. It's upper division mathematics kind of stuff. Okay, so we're not doing it. The good news is all you have to do is know if they say, what is a test statistic? You write this down. Sound good? And I'd like to show you the picture because that gives you an idea of what's going on. The math is too hard. And then the p-value, and I do want to mention something. The p-value is 0.05. I did not give you a level of significance. Did you need one? Yeah, the answer is you don't need a level of significance. How come? Yeah, you don't even have to assume it's 5%, but the idea is 0.5, which is 50%. That is bigger than any level of significance anyone would ever use in statistics. So you don't need it. It turns out that in the real world, I like to tell you real world, especially towards the end of the class, because, when you leave this class, that's all you got left is real world, right? It's using stats in the real world. No one's going to give you the level of significance. So if they don't give it to you, you have to look at the p-value and then kind of analyze it. Here, it's clearly statistically insignificant. If the p-value instead was let's say it was 0.08, that's bigger than 0.05. It's not bigger than 0.1, and you would say there's weak evidence. You kind of use the word weak, and there's evidence, but the evidence is weak. It's not strong enough to be under the 5%. And that's typically what you say. Whereas if the p-value was, say, 0.02, then you would say there is statistically significant evidence, but you wouldn't use the word strong. If the p-value is, say, 0.0004, then you could say there is strong statistically significant evidence. Do you see how that works? So sometimes you use language, and that tells those who are at least statistically educated what it means. But 0.5 is never going to be significant because you're way, way past anything anyone would ever be okay with. Any questions on that? Okay. Let's do one more example. A study was done asking people how far they plan on traveling for Thanksgiving. Okay, we got Thanksgiving coming up. Hopefully you all know that in 9 days. And the mean was found to be 120 miles. The standard deviation was 40 miles. Sound good? The table shows some results. Okay, now this is a quantitative study, but I'm changing it a little bit of thinking. And let me erase these because I want to show you how we got these. Whoops. There we go. Okay, so the observed in this study that was imaginally done, there were 56 people that answered under 80. There were 61 who answered between 80 and 160. And there were 12 who answered higher than 160 miles. See how that works? All right, so now what we want to do is, the question is, do we have a normal distribution? Any questions on that idea? Okay, in the past, what we did is we drew a histogram and we kind of eyeballed it and we said, well, it kind of looks normal. Do you remember doing that? Okay, project 1, you were supposed to do that, right? The problem with it kind of looks normal is that's about as non-mathematical as it gets. Okay, and we want to be able to, mathematically test normality. Any questions on that idea? So one way of testing normality. Yeah, good. So your idea is, do we have to use the 2 standard deviations as about 95% of the distribution? And that's exactly what we're going to do. Okay, 2 standard deviations. But actually with my example, I'm going to look at 1 standard deviation, but you get the idea. So you can test normality with just 1 standard deviation. You could also do 1 and 2 and 3 standard deviations on all sides, test it with a much bigger chart and to be more sophisticated, and you can do that too. I'm going to try and simplify things and make it an easier way of looking at it. And that's just 1 standard deviation. So to do that, what I can do is I can say, does this data fit the normal distribution? The normal distribution is a known distribution, right? It's very well known, it has a beautiful formula. At least if you're a mathematician, you think it's beautiful. If you're not, you may think it's ugly. But I think it's a beautiful formula and a good shape and all that. So we can test if this unknown distribution of miles traveled for Thanksgiving, does that fit the known distribution of being normal? Any questions on that? So I'm going to use the goodness of fit test because to see if an unknown distribution fits a known distribution, that's goodness of fit. Any questions so far? All right, so now I need to write down my null and alternative hypotheses. What word has to be there for goodness of fit? I told you there was a word that had to be there for the null hypothesis and the alternative hypothesis. Remember that word that had to be there? Yeah, distribution. So I'm going to write the distribution of miles travel for Thanksgiving is normal. Isn't that easy? Because that's what we want to see, is a normal distribution. And very easy, once you know H naught, very easy to write H1. Hopefully you're used to that with this chapter. I can copy and paste, and what word do I have to add in? Very simple. Yeah, not normal. It's either normal distribution or it's not a normal distribution. Any questions on that? All right, so now notice that the mean was 120. The standard deviation was 40. It's not a coincidence that if I take 120 and subtract 40, I get 80. And if I take 120 and add 40, I get 160. I did that to make life easy. So what this is, to be between 80 and 160 is saying we're within 1 standard deviation of the mean. Is that clear? What percentage of the data is between 1 standard deviation of the mean if you have a normal distribution? See if you can remember that kind of rule. The empirical rule, we called it. Do you remember the percent within 1 standard deviation? I know it's been a while since we thought about it, but it came up. 68%. You were really close though. Okay, so 68% of the data falls within 1 standard deviation of the mean. So if we want the expected for this between 80 and 140, by the way, the sample size was 129. All we do is we're going to take the 129 times 0.68, or 0.68 times 129. Unlike the last example, this one I can't do in my head. But what I can do, I'm very good with putting it into a calculator. And you get, whoops, 0.68. There we go. 87.72, and we should round because it's a number of people. So I'm going to use 88. And just to make it easier to read, let me write 0.68. All right, how much is less than 1 standard deviation? What percent? And remember? Yeah, 16% is less and 16% is more. Remember, if there's 16%, if there's 68% in the middle, 1 minus that is, or 100% minus that is 32%. 32 divided by 2 is 16. So if I'm going to take 0.16 and multiply by 129, let's do that. I get about 21. So we would expect to have 21 less than 80 and also 21 greater than 160. It's symmetric. Any questions on how I came up with the table, the observed and expected table? The observed was just data collected, by the way. Now that I just had it put in.
I do have a, well, so I know that you can't really have like half of a person or a fraction of a person, but since they sum to like 1 less or 1 more than,
Yeah, that's called round off error and it happens.
would it be still acceptable to like keep the decimals in because it's about the distribution and not like the wholeness of a person?
Yeah, honestly, I think I'm not even going to go there because in the real world, you would actually do a whole lot more.
Okay.
You would actually not just look at 1 standard deviation. You would look at many different brackets, not just 3.
Right.
And then you have to do some rounding. I think I'm not going to go there. There's elementary stats side. Sorry about that. So you cannot round if you want. Eventually you got to round. But again, it really doesn't make a big difference in the p-value. That's the good news. As long as your sample size is big. And notice these numbers are much bigger than 5. And you got to have that. If you don't have bigger than 5 for the expected, you're in trouble. Okay, so now I am going to go back to the calculator. And we're in goodness of fit. And the observed, we're 56, 61, 12. I can copy and paste it in. And the expecteds, we're 21, 88, 21. And I calculate. What do you see? Is a p-value 4.44 about?
Isn't that inordinately high?
What's that?
Isn't that way too high? Oh wait, oh, negative 16, so that's very
Yeah,
low.
and I want to highlight that. I want to highlight that. The p-value is not anywhere close to 4.44 because this e negative 16 tells us that we need to move that decimal over 16 places to the left. So the p-value is about as close to 0 as you can ever get. Does that make sense? This is as strong statistically significant evidence as you can get. So there is very clear that H1 is true. Okay, so chi-squared, I should write it was 70 or so. 70 or 71 was exactly 70, good. And then close to 0 for the p-value. Basically, as close to 0 as you'll ever see. So we conclude. And we do the conclusion. Let me make it big enough. And hopefully you all know if the p-value is as close to 0 as it gets, what is the conclusion? What's the first few words? I'll start with there. Yeah, and I'm going to even, this is when you get such a small p-value, I'm going to write is very strong statistically significant evidence. That, and then the distribution of miles traveled for Thanksgiving is not normal. I'll copy and paste it in. Yeah, it looks like this needs to be a little bigger. There we go. Any questions on this example? Any questions? Okay. By the way, this does not tell you what the distribution is. It does not tell you it's uniform. Just because it's not normal does not mean it's uniform. Doesn't tell you it's skewed left or skewed right. Just tells you, we just know it's not normal. And that's as far as we know from that. Any questions on this idea? Any questions? What do you think the hardest part of this chapter is going to be? And by the way, my definition of hard is people get it wrong on the assignments, the exams, and the discussion assignment. What do you think the hardest part typically is? Any thoughts?
Let's say using the right test.
Yep, perfect. Yeah, deciding which test to use. Okay, so deciding which test to use is usually the hardest part because you have to say, you got a paragraph of stuff. It's not going to say, use goodness of fit test. You're going to have to know to use a goodness of fit test based on the circumstance. So let me just review a little bit. If you want to find out if a distribution is of some sample that represents a population, but you only know the sample, is the same as some known distribution like normal, uniform, or something given, then that'll be goodness of fit. Okay. And we're talking about, qualitative studies. It may look quantitative, but it really becomes qualitative as soon as you say less than 80, between 80 and 160 and greater than 160, because you can think of this as kind of left side, the middle, and the right side. Do you see that? As soon as you write it this way. So then you're going to use goodness of fit. Whereas if you're comparing two different distributions, which you don't know either of their populations, then that's homogeneity. And if you have two survey questions where they're both qualitative answers, and you want to find out if they're independent or dependent, or another way of thinking about it, is there a relationship between the two? Then we're talking about test for independence. Any questions on that idea? Any questions? Okay, and there's lots of words, and hopefully you get used to that in this class, right? This class has more words than any math class I ever teach. Any questions at all on any of these types? Okay, and the last thing is the secret word. And the secret word is known. Because when we're looking at a good as a fit test, we want to find out if an unknown distribution fits a known distribution or the known distribution. So that's why I gave you the secret word as known, K-N-O-W-N. And that's pretty much all I need to talk about for good as a fit. Again, there's not too much to talk about the project. I'm always happy to answer questions. I am going to stop the recording because I'm done talking about new material. So let me do that.